The term composition is commonly used to describe features of innumerable materials and products in almost every aspect of our world. It describes simple and everyday things, such as just how we like our favourite refreshing drink. Of course, when making drinks, we can try to use the method that results in the taste we prefer. If we are making drinks for customers, it is important to make them taste the same every time. For each specific drink, this clearly means using the same ingredients and the same method or process to make it. We can name branded drinks available practically anywhere whose compositions are secret. A drinks company is likely to make a variety of drinks. They will need to describe the composition of each one in an objective, scientific manner. Of course, drinks may generally be described as liquids, but some things based on liquids are more complex. This nutritious soup is basically water, but its taste depends on the exact combination of things added. Some products made as a liquid can appear more solid when chilled. Thinking of products in general, it is clear that composition can affect a number of other properties. Homogeneity describes how evenly mixed a product is, even if it contains several materials. Concentration tells us how much of a specific material is present. Suspension describes a fine particle material mixed into a liquid so that it stays suspended over time. Rheology describes how a material behaves when we apply motion forces. For example, when stirred, some materials will stiffen, but others will become more liquid. We will explore 3 contrasting application examples where composition is critical. We will also see how multidimensional sensing can help us to ensure that composition meets our requirements.
Our first example continues our food theme. When we're in a hurry in the morning, our light breakfast may be strawberry yoghurt and a nut bar. Strawberry yoghurt seems straightforward, but it is difficult to repeatedly get the composition perfect. Each batch and each portion must have the right amount of fruit in every pot and the right amount of mixing. We don't want fruit parts to be too big, but we don't want them totally liquidized, as in baby food. We can imagine a simple process for making fruit yoghurt based upon a few key parts. We hold the 2 ingredients, plain yoghurt and mashed strawberry fruit, in separate tanks. The tank outlets are fitted with control valves so that we can adjust the mixture. Each tank has a separate pump to pressurise the flow so that the 2 parts combine at the union. The resulting simple mixture is passed through an inline mixing device. Here we see a selection of such mixing devices, all designed to break up large parts and make the mixture more homogeneous. We adjust the control valves to settings based upon experience or by trial. After mixing, the resulting product is then ready for packaging. We cannot see inside this process, so it's difficult to control the various composition parameters to ensure perfect consistency. If we could look inside, we could check that our products meet our requirements. Our multidimensional sensing methods are useful for this purpose, as they can provide an estimation of the composition. To gain optimal information, it is useful to see the composition of the combined raw materials and the mixed result. We can place a sensor at each of the 2 points as shown. The tomographic sensors are designed to fit into the pipeline. Here we see an external view showing the end coupling flanges and the sensor connections. Each sensor has a ring of 16 internal electrodes. This unit also allows clean in place use, denoted by the CIP marking, a requirement for food processing. Here we see the monitoring system display showing images produced from the twin sensors. The false colours here represent the sense value of conductivity at each pixel. The band of colours indicates the range of composition. On the left, we now see the inlet raw materials are segmented. On the right, we see a well-mixed product. In both images, we see the pulsating action caused by the pumps. The data can also be shown in 3D over time, depicting the variations in composition mixing. We can produce interpretive data that shows the flow at each sensor over time, indicating any changes in product composition. We can use this data for process control and for logging product composition records, to track batch variations. In conclusion, seeing inside can deliver improved control and monitoring increasing quality and reducing waste and energy consumption. For our second contrasting example of critical composition, we begin in Hong Kong with its busy international port. This example concerns the global industry of channel maintenance and landforming in the management of the interface between land-based facilities and the world's oceans and seas. Here the maintenance of shipping lanes is critical to safe navigation. Landforming also enables major man-made features. The famous children's story of the little Dutch boy who put his finger in a hole in a dike and prevented a flood illustrates how carefully we must manage structures at the ocean to land interface. Because the Netherlands are low-lying, the Dutch people have become expert at forming new land from the sea. But this is not easy. We'll explore landforming and what is needed to make it efficient and effective. We begin our exploration on a road in a modern city. Looking around, we see new road developments and monorail transport. Imagine looking down from a helicopter as we ascend to get a wider viewpoint. We see the rooftops of buildings and the general road infrastructure. We now see water inlets appearing at each side of the roadways and buildings. As we ascend, it is becoming clear that this place has a precise structure and has been man-made from the sea. We begin to recognise that we are above the man-made Palm Island on the Persian Gulf coast of the city of Dubai. Climbing higher, we see the whole coastline and the major landforming to create the two Palm Islands and the World Islands. Major work has been done in Dubai, but landforming actions are worldwide. A simple way to create new land utilises a ship that can pump seabed material and precisely direct it to a target site. A typical ship is able to pump 30,000 tonnes of material per hour from its spray tube, which has a typical diameter of about 1 metre. For efficient and safe operation, continuous measurement of the density distribution of the mud and water slurry is critical. Too much water will cause the material to diffuse away from the target site. Too much mud will cause pump overloads and reduce projection range control. In the past, density sensors have exploited a radioactive gamma ray source. These have major safety issues, need periodic replacement, and can cause long delays for certification as the ships move between countries. Companies are replacing their gamma sensing units with electrical tomography sensors to eliminate these problems. The non-intrusive sensor is simply inserted into the slurry feed pipe. Control of the raw material flow is essential to provide optimal effectiveness and efficiency. A control panel provides information on slurry flow rate and composition to enable precise control of pumping and deposition. Sophisticated features provide detailed current performance and trend logging for all critical parameters. At the upper right, we see the current time and selected log parameters, concentration, density, and flow velocity. At the upper left, we see the recent time log for the selected parameter data. At the lower left, we see the current cross-sectional composition. The summary data value also appears in the lower right performance display. Along the bottom of the display, we see the corresponding time log, composed of the vertical centre line of each cross-sectional slice. The corresponding current time for this log is at the lower left end. We expect the data to appear to move right. At the lower right, the performance display provides key information for control and monitoring. We see the velocity is 2.5 metres per second. The production rate is about 3 tonnes per second. The solids concentration is about 25%. And finally, a calculated efficiency value relating pumping energy to material delivered is 70%. The green key parameter pointers give instant information of solids concentration and flow velocity. We can now see the unit in action for a short time, showing how the left composition estimate is reflected in the data logging and control information. In summary, The multidimensional sensing data is used to deliver key information to make both channel dredging and landforming operations effective and efficient. For our third contrasting critical composition example, we begin by visiting a nuclear power station located near the UK coast. There is no sign of obvious emissions. There are no chimneys causing pollution and emissions such as CO2. Nuclear power is claimed to be our cleanest form of energy. Once loaded with nuclear fuel, a reactor can produce heat energy, used to generate electricity for several years without any emissions. Our present highly developed nuclear technology exploits a controlled fission reaction. This transforms one form of uranium to several other mostly radioactive fission elements, plus massive heat energy. The fission byproducts must be separated so that they may be reused or stored in the safest way. This is carried out at a nuclear reprocessing plant. The operation of processes at such sites is tightly regulated. Each process is certified and must be monitored continuously to ensure compliance with stated operating conditions. One such certified process is concerned with combining a heavy metal dissolved in nitric acid with a further reagent that allows the separation of the radioactive compound for safe storage. The process shown in schematic form exploits a vortex that forces specific materials to the rim, separating them via the outlet. The level of the vortex is dependent upon the stirring speed as well as material composition. Continuous monitoring is required to confirm the presence of the stable vortex. For this we require to see inside this heavily shielded and protected process. The process includes a linear probe to sense the state of a vertical cross-section. The structure of the probe can be seen more clearly in close-up, showing its 18 electrodes. The probe data can be used to derive a radial section tomographic image of the estimated composition. We can set the impeller at a slow speed of 200 revolutions per minute and use the probe data to derive an image using appropriate software. The resulting tomographic image is valid for an approximate region up to the vessel centerline, as illustrated by overlaying the actual image on the diagram. We see no discernible vortex at the slow speed. We can increase the impeller to a higher speed of 300 revolutions per minute and derive a further image. We now see a modest vortex. Now a further increase to 400 revolutions per minute. We now see a deep and well-developed vortex. With further processing, we can use the data to specifically estimate the most likely location of the vortex boundary. We now see an unambiguous vortex location. We can also assume and exploit vertical axis symmetry. We now see the whole vortex, providing the basis of an effective tracking instrument. We can experiment with a range of speeds using this interpretation method, as shown in images below the diagram. As expected, we now see a clear linkage between impeller speed and vortex depth. We must also be aware that vortex depth will also be linked to composition and density of the process materials. We are now ready to design the features of a vortex tracking and monitoring unit. We see set threshold controls, a view of the current estimated vortex at the left side, a status information display at the right side, and a log of the vortex status at the centre, plus a number of warning indications. We can explore operation using actual process data. The data shows a progressive increase of the vortex depth, from a shallow state, eventually to an excessive deep state. This may call for a controlled reduction in impeller speed. To summarise, even simple multidimensional tomographic sensing provides a unique and valuable insight into this difficult to manage process.
Practically all food products are formed from multiple ingredients, where consistency of composition is essential. Measuring multidimensional composition in food production processes provide a step up in information, quality, and production efficiency. Sophisticated civil engineering structures require high quality materials to ensure strength and uniform properties. Measuring composition in volume provides assurance of consistent composition and increases quality and yield, reducing energy and emissions. Chemical processes require high quality information to monitor reactions for improved products and reduce costs and negative impact. So in summary, industry in general is continually pressured to enhance its performance. Business drivers press for improved productivity along with product quality and increased return on investment, such as process plant. Environmental drivers press for reduced pollution and waste. Energy drivers press for reduced energy consumption and emissions. We can classify and examine these various pressures and drivers in more detail. Here, the red circle represents business pressures which seek higher, bottom-line benefits. Our multidimensional sensing technology provides key insight to provide composition information to enhance process performance, leading to higher utilization, product quality, and safety. The green circle represents fiscal and societal pressures to reduce impact on the environment. Our technology provides advanced composition information leading to reduced waste and impacts. Finally, the blue circle represents pressures to reduce energy consumption and global warming emissions. Enhanced composition information aids efficiency gains and reductions in energy usage and emissions. We've been working with images. As any schoolchild knows, mixing red, green and blue light gives white light. This analogy illustrates the resulting red, green and blue potential process improvements we gain through enhanced composition information from process sensing technology, represented by our white outcome circle. In summary, super sensing composition information delivers enhanced processes.